Okay, so hello everyone. My name is Saif Aldabagh, and I'm currently a postdoctoral research fellow at the University of British Columbia. And the title of my presentation today is the seismic performance of retrofitted and repaired bridge column under major and several aftershocks. So this work was led by my colleague Musharraf Hussain, and it was done under the supervision of Dr. Shahriala of the University of British Columbia. So the outline of my presentation today is that we will start with an introduction, just by giving you a little background of the topic, and then I will move to the experimental investigation, where I will describe the test matrix, and then I will present a series of tests that were performed to determine the properties of the GFRP sheets that were used in this experimental program. And then I will present the test setup and instrumentation, and then the repairing procedure that was adopted. And then we'll move on to the results. Yeah, so as many of you know, that the FRP composites jacketing has been one of the most common retrofitting technique in North America. And research work evaluating the performance of bridge columns retrofitted and repaired with GFRP jackets has been common. However, research work focusing on the performance of such bridge columns under repeated cyclic loading has been limited. And this type of research is really critical, in particular when considering the lane shock and aftershock effects, which is the focus of this study. So in this experimental program, two identical bridge columns were built. And these bridge columns were basically a 1/3 scale models of a seismically deficient bridge column and bridge Columbia. And this is the prototype. This is the prototype bridge that was adopted, and this is the test specimen, which is basically, as I said, it's 1/3 scale model of the prototype bridge. And the main deficiency of this bridge column was the widely spaced spirals, which was used in this bridge column. It was 100 millimeter spacing of the spiral in this bridge column. So basically, we built two bridge columns, and the first was tested as in terms of the as-built condition, and it was designated as the deficient specimen. And that specimen, after it was tested, it was repaired with the GFRP sheets, and then this specimen was tested again and was designated as the repaired specimen. And then the second specimen was retrofitted, and then it was tested, and hence it was designated as the retrofitted specimen. So basically, we had 3 specimens tested, but actually we built two bridge columns. So in the beginning, we performed a series of tensile tests, compound tests on the GFRP sheets to determine their properties, and also we performed bond tests to determine the optimal overlap length. And the results of those tests are shown here. We consider different thicknesses starting from 1 layer to 3 layers. And this figure here shows the tensile strength versus the strain responses. And as you can see here, with the increase of the number of layers, we had higher stiffness and higher strength. And when we moved to the bond test, we found that after certain overlap length, the gains in terms of bond strength becomes minimal. And based on this observation, we have determined that the optimal overlap length would be a 150 millimeter. So in terms of the properties of the GFRP, you would notice that the tensile strength of the GFRP is more like on the lower end of the typical tensile strength of the GFRP. And the reason is that the type of GFRP that was used in this study is designated as low-grade GFRP. And it's available here in the local markets, and it's mainly used for strengthening applications in marine systems. So this figure here shows the test setup, and it's typical or standard cyclic test that was performed. And just to give you an idea about the main elements here, the post-tensioning rebar was used to apply the axial load, and the LVDTs were used to measure the curvatures, and strain gauges were installed on the longitudinal as well as the transverse reinforcement in the plastic hinge region. So in terms of the applied loading protocols, we have applied two set of loading protocols. The first was basically an individual loading protocol. And the second set were like repeated loading protocols that were applied to the bridge columns to mimic the effect of the aftershocks. After testing the deficient bridge column in the as-built conditions, we had to repair it. And then here I'm showing pictures of the repairing procedure that was performed. So this is the this picture shows the damaged pier, and you can see that the buckling was quite significant because of the widely spaced spirals. And then the first step was to apply vertical support and then remove the axial load effect. And then a framework was prior to putting the framework, we had to do some restoration for the and repair for the buckled rebars. And then we had to put a formwork to pour the repair concrete. And then this picture shows the repaired concrete. And then the surface was treated prior to the installation of the GFRP sheets, which are shown in the. So this is the final condition of the repaired bridge column. So the tests were, as I said, they were at two levels. The first were at the material level, where we had cylinders tested under compression, and then these cylinders had different. Basically, we had two different types of cylinders: the type 22, the control, and the type 32 control. The first had the concrete compressive strength of 22 megapascal. The second had the concrete compressive strength of 32 megapascal. And also, we looked at the influence of increasing the number of layers of GFRP sheets. We had 1, 2, and 3 layers, and with the increase, as you can see in this, the compressive strength versus the axial strain, that the increase in the number of layers resulted in increasing the strength as well as the strain capacity of the concrete. Moving on to the results of the column testing, as you can see here that the deficient column experienced premature strength degradation at early drifts, which were about 4%, and this was mainly because of the initiation of the inception of bar buckling in the plastic hinge region. And when we compare it at the performance of the repaired and the retrofitted bridge columns, we can see the gains that were attained because of the confinement from the GFRP sheets. There were significant increases in the strength, and the rebars were able to sustain drift ratios up to 6.9% without experiencing any strength degradation. And this table here shows that the strength gains were 25 and 27% for the repaired and the retrofitted bridge columns, respectively. So after performing after applying the first set of, or the initial set of the loading protocol, the first loading protocol, we applied a repeated loading protocols to evaluate the performance of the bridge columns under basically repeated cyclic loading. And the repaired specimen was able to sustain only a second loading protocol, whereas the retrofitted bridge column was able to sustain up to 6 loading protocols. And these two figures here show the envelope of the force versus displacement responses. And as you can see in both cases, after applying the first loading protocol, there was a reduction in the strength. And in the case of the retrofitted bridge column, the degradation continued up to the fifth loading protocol. In terms of the energy dissipation, we also looked at the relationship, the influence of the applied loading protocols on the energy dissipation. And as shown here, like in both cases, the repaired and the retrofitted bridge columns, there was a reduction in the dissipated energy for both cases. However, like after the first loading protocol, the differences were not as significant in terms of the reduction in the dissipated energy. These figures here show the failure modes that were observed. The prime reason for the failure was that the GFRP sheets developed their ruptured tensile strain capacity, and this is shown here, and also it was shown in the retrofitted bridge column. It's shown here. And also another reason for the failure was the horizontal rupture under compression, which was observed in the two cases. So the key conclusions that were observed from this study is that concrete confined with the low-grade GFRP that was considered in this study exhibited noticeably higher compressive strength and ultimate strain than unconfined concrete. The repaired and retrofitted reinforced concrete bridge columns were characterized with enhanced capacity, ductility, and energy dissipation when compared to the deficient specimen. The GFRP retrofitted column showed better performance than the repaired ones when subjected to repeated cyclic loading protocols. Thank you, and I would like to take your questions.
Thank you, Saif.
Hello, I have a question about thickness of the GFRP sheets that you have used. Did you carry out any sensitivity analysis with the variation of the thickness of GFRP jacket during your study?
You mean like when we did the test at the material level or at the like the member level for the cyclic test?
The member level, yes.
Oh, the member level, it was 2 layers, so it did not change. We tested just 2 columns, with one was repaired and retrofitted, so we haven't varied the thickness of the GFRP layers in these tests, except for the material level, where we looked at the 1 layer, 2 layer, and 3 layers.
Okay, thank you. Thank you so much.
Okay, I can ask you one question. Saif, if you can go to that those envelope curves that you are presenting.
Yeah.
Yeah. For example, if someone wants to understand, the main shock aftershock sequence and try to analyze in software, like how you can say that these curves could be helpful for the practitioners.
Yeah, so like one of the important outcomes of this study is to have certain data to validate or to create a numerical model, like at a later stage, which could capture the degradation of the influence of the repeated cyclic loading. So, for example, if we do create a numerical model now, we would be able to capture the behavior that is resulting from the first loading protocol. But that cumulative damage effect that results from the sequential applied loading protocols, in order to capture it, it would be useful to have these data in order to capture that degradation that's caused by the applied loading protocols. So this is one of the so this is why the data is valuable for a later stage, where we could create a numerical model that captures the degradation in these protocols.
Okay, thank you.